So I'd like to welcome you to our April meeting of the North Jersey Astronomical Group Astronomy Club. We're a week late because last week we were not all of us, many of us were away for the total solar eclipse of the sun, and we're traveling or about to travel to come back to New Jersey. Tonight, though, we have some people who are going to tell us about the ways that we can see and investigate the sun without having a total solar eclipse, although that was very exciting, I think. So Arnaud Thernisien and Damien Chua are from the Naval Research Lab in Washington, D.C., and they're friends of my friend, Yadira Padilla, who I met last year at the Adirondack Astronomy Retreat in upstate New York in the Adirondacks, almost on the shore of Lake Champlain, where we go for dark sky observing. At any rate, they're going to tell you a little bit about themselves and then about how we can observe the sun and its active corona.
Thank you, Mario. Yeah, my name is Arnaud Thernisien. I work at the Naval Research Laboratory in Washington, D.C. I've been working there for more than 20 years now. I studied physics in Lille, first in north of France, University of Lille. Then I went to Marseille to study engineering and optics, image processing. And that's also where I got my PhD in the University of Marseille. I guess I was always interested by physics. When I was in high school, I thought the coolest uh, uh, professors were the physics professors. They were a little bit crazy, I thought. So that's why I got into physics, I guess. Um, and then, yeah, I started to work in the laboratory of Marseille, um, which designed one of the instruments that we will present here, our chronograph. And then I came to work at the Naval Research Lab, I think in 2003. I thought I was going to stay there for 1 year, and I've been there for 20 years. So I guess I like it here. And I'm now the principal investigator of the CCOR compact chronograph. That's a chronograph that's designed to uh, do space weather predictions for NOAA. And maybe Damien can introduce himself to.
Great. Well, thank you for having us for this meeting. I'm Damien Chua. I have also been at the Naval Research Laboratory for about 20 years. I started there as a postdoc in 2002 and became a Fed in 2004. My entryway into physics and astronomy was really I think as a freshman and undergraduate, I came into college thinking that I wanted to pursue law, but it just took one really excellent physics professor in freshman physics to turn that around. So the rest is history, as they say. So I had a summer internship as an undergraduate in our physics department at the University of Puget Sound in Tacoma, Washington, where the physics department had just installed a observatory on the rooftop. So it was really just a small 8-inch Schmidt-Cassegrain telescope. And I had a summer project to make photometric observations of variable stars and to try to make some light curves. I think I ended up settling on Beta Lyra as the star that I looked at all summer. So that was kind of my entryway into astronomy. And then after college, I spent some time at the High Altitude Observatory in Colorado in Boulder as an intern, that's kind of where I got my introduction to space flight hardware, and then followed that up with my graduate work at the University of Washington in Seattle, working in the Department of Earth and Space Sciences, where I got my PhD, specializing in space physics, but magnetospheric physics. And somehow over the years found my way, turning my attention away from the Earth's magnetosphere to the sun and really the heliosphere. So, but we'll talk about those connections in this presentation. So that's how we get to space weather.
Okay, thanks, Damien. So I guess I will take it from here, unless there are other questions. I will present half of the presentation, and then I will give the microphone to Damien, basically halfway. So again, well, welcome. This is I'm going to talk about observing the sun and its active corona. So, well, the sun, that's how you observe it in the visible. No sun, no life. The sunlight is really the source of our life on Earth. And this is on the right how you see it in white light. And you need glasses, of course. If you've been to the eclipse, you cannot watch the sun without a CIUS filtering glasses. And sometimes what you can observe on the surface of the sun is these small dark areas, sunspots. And these sunspots are due to the magnetic activity of the sun. So the sun, a little bit like the Earth, there is a dynamo effect that creates a strong magnetic field on its surface, and that as a result, you can observe these sunspots, and we will see other effects, various effects. So the sun can be seen in various wavelengths, meaning colors. For example, here, if you use a red filter, H-alpha filter, the H-alpha is related to the hydrogen atom, and you will see more structures at the surface of the sun, and maybe even some prominences, some sort of cloud of plasma levitating right above the sun surface. The sun surface is roughly at 6,000 kelvins of temperature, and we'll see that its atmosphere it's at a vastly different temperature. Now, if you're really lucky, meaning at the right place at the right time, you might experience a solar eclipse, and that's probably for the luckiest of you last week. You were able to experience that. And this is when the sun, the moon, and the earth are perfectly aligned. And then the moon will cast a shadow, a small shadow on the surface of the earth. And if you are right inside that shadow, well, you don't see the sun disk anymore, but what you see is that sort of cloud, foggy cloud around the sun and the moon, which is the solar corona. It's actually the atmosphere of the sun, if you want. And that solar corona is the result of the scattering of a very hot plasma at the surface, well, at the surface, starting from the surface of the sun and towards the rest of the space, basically. That plasma is highly shaped, as you can see here in that very nice eclipse picture taken in 2019. It's the result of electrons, which are charged particles, and they are aligned with the strong magnetic field of the sun. That's due to the, again, dynamo effect of the sun. And these electrons, they follow the field lines of the magnetic field, just like iron filings would follow the field lines of a magnet, for example. So during an eclipse, you can see the corona up to roughly 3 solar radius, a little bit more, if really you are in perfect conditions, meaning with very low humidity, with some elevation, maybe at the top of a mountain. But you are kind of limited in the extent where you can observe the solar corona. So again, what do we see in the corona? Well, as I explained earlier, you have first the K corona. You have two components, really. You have first the K corona, which means continually. It's a German word, okay? So that's the result of Thomson scattering of the sunlight by the free electrons of the plasma. So that plasma is very hot. It's 10,000 kelvins, I think. So it's much hotter than the surface of the sun. And that's still a main subject of research to understand why there is such a difference of temperature between the surface of the sun and the solar corona. So that K corona is active, and it is strongly shaped by the magnetic field of the sun, and it's active because it moves. It can vary very quickly, as we will see later. And it dominates the K corona dominates the solar corona very close to the sun. But on the other hand, as you move away from the sun, it's then dominated by the Fraunhofer corona, or the F corona. That corona is the result of the scattering of the sunlight by dust, the dust that surrounds the sun and the rest of the solar system, basically. It is not shaped by the magnetic field and does not vary. And again, the F corona dominates what you see from the corona above 3 solar radii. And one thing important is that both components are optically thin, meaning you can see through it. And here I show like the spectrum of the sun, and you can see the peak of the spectrum is in the visible, but as you can see, there is also some light in the UV and lower in the infrared. And the way scattering works, the sunlight illuminates, let's say, some electrons in the K corona, and these electrons will scatter some of that light back to an observer, to our eye, if we are experiencing a solar eclipse on the ground, or here it could be a telescope or a spacecraft in space. Now, why we need to wait for an eclipse to see the corona? Well, it's because on the Earth we have air, and the air scatters and gives us the blue sky, and that blue sky has a brightness that's about the brightness of the solar corona. In that plot, I show the brightness of the K and F corona. Here, the K corona is in dotted line, and the F corona is in more solid line here. It's a logarithm plot, so the vertical axis is the brightness, and each unit here corresponds to one order of magnitude, or a factor 10. So you see the blue sky is basically at 6 orders of magnitude lower than the sun itself. We take the solar brightness as the reference brightness. We say that the surface of the sun is one solar brightness. And the blue sky in a normal day is about six orders of magnitude less bright than the sun itself. But because the solar corona is less bright than the blue sky, well, we just cannot see it during a normal day. We have to wait for an eclipse. And when that eclipse occurs, it will drop the blue sky by 3 orders of magnitude. And then it reveals the solar corona, let's say here, up to 4 or 5 solar radii. That axis here in X is the distance from the sun in solar radii. So that explains why you have to wait for that eclipse to see the corona. Unfortunately, the eclipse occurs only once. They're very rare and local. They occur every 18 months roughly. So if you want to observe it on a more regular basis, daily basis, you have to use what is called a coronagraph. And a coronagraph is an instrument that creates an artificial eclipse of the sun. So it will block the sunlight, and it allows you then to observe the inner solar corona, so the corona that's very close to the surface of the sun, because you still observe that from the ground. So you still have the sun, the blue sky. But here, I show a small movie of the first coronagraph that were designed by Bernard Liot in the 1930s. And as you can see, you can see these very nice prominences evolving right above the surface of the sun. This is in white light, in visible light, and for the people that saw the eclipse last week, you could see a small prominence, I think around 7 o'clock on the disk. Note that this movie has been accelerated by, I think, more than 10 times. So again, these phenomena are much slower, but here for the sake of the movie, you can enjoy seeing everything moving in a reasonable time, basically. A few words about the design of that coronagraph. It's a basic refractive telescope, and there is a first lens here in front that creates an image of the sun on a disk D1. That disk D1 acts as the moon, if you want, and will block the direct sunlight and will only let in the instrument the corona, which is what's above the surface of the sun, on the limb of the sun. There is a relay lens here, O3, that creates then the image of the corona on a focal plane, or maybe on an eyepiece, if we want an observer to look at the corona in real time. Note that there are various devices here to reduce what we call stray light, because again the sun is one solar brightness, and we want to observe a signal that's more than or less than 6 orders of magnitude than the sun itself. So this is very challenging, and you have to have some various design tricks, if you want, to reduce that stray light that would otherwise mask the solar corona that you want to observe. During World War II, so here I'm trying to, I will make the link between, we're often asked why at the Naval Research Lab we look at the sun. Well, this is the connection, is that during World War II, a solar physicist of the Harvard College Observatory, Walter Roberts, observed that the change in the corona were affecting the radio communications on the ground. So he concluded that these changes of the solar corona would provide some advance warning on various communication disturbances between ships, for example, on the ground. And this is this was obviously critical during wartime, and this is why his research was overseen by the Navy starting during World War II. And note that the Harvard College Observatory was later renamed High Observatory, HAO, so High Altitude Observatory. Or maybe one last thing on that movie that I forgot to mention is you see these that magnificent, I mean, that's really amazing prominence erupting here. So what you can observe with this coronagraph is that, again, the sun is very active, and this prominence, sometimes they seem to levitate above the surface of the sun, but sometimes they really erupt and are, go away in the outer space. And this is what we call coronal mass ejection. So again, like its name says, it's mass that's ejected from the corona that goes in the outer space. Here, that's another example of the scale of this phenomenon. This is observed in UV light by, I think, SDO probably, which is a NASA telescope. And that shows the size of the Earth compared to the scale of this phenomenon. And again, this is huge, huge phenomenon, basically. Well, if we only observe the corona from the ground, we are limited, as I mentioned earlier, in how far we can observe the corona. So we have to wait for eclipses, or maybe with a coronagraph, you're very limited to maybe 2 solar radii maximum, and that's it. So the only way to get rid of that blue sky and even eclipse sky is to go to space, where you have no more air scattering, basically. And this is what was done starting in the early 60s. First with using balloon-borne experiments, where you can go very close to space, or sounding rockets. And finally, some satellites in the later 60s. And that's when basically they first observed that these ejections that they could observe very close to the surface of the sun were actually propagating away from the sun in the rest of the solar system, basically. And the first coronal mass ejection that was observed by that spaceborne coronagraph was, as the legend says, at the Naval Research Lab, was observed by an electrical technician, Dave Roberts, that was looking at the data from his camera, the camera that he designed, and he saw a brightening on some images. He initially thought that his camera was broken, or there was a problem with the camera. But after more investigation by his supervisors, they found out that this was real, and this was an actual ejection of mass that was propagating in the field of view of that telescope. Yeah, there were successive missions and coronagraph along the years in the 70s. And one mission that really is really a milestone was the SOHO mission that was launched in '95. About that, it is still an ESA-NASA joined mission. And aboard that spacecraft, there is the LASCO coronagraph. That's these days, basically, it's still working. So almost 30 years later, and that coronagraph is still used nowadays by NOAA to do some space weather predictions. So this is an example of a movie observation from LASCO coronagraph. It's a combined movie from LASCO C2, which is the inner field of view, and LASCO C3, which is the outer field of view. That's why you have some sort of a seam here. But as you can see, maybe I will go back to the beginning of the movie. At some point you have here we go. Here you have what's called a halo CME, which is a coronal mass ejections that basically looks like concentric circles and is generally directed towards the Earth. And if we look at that again, sorry, the beginning of the movie, you see that right when the coronal mass ejection starts, you also have a bunch of snowflakes on the image, and this is some very high energy particles that are released from the surface of the sun and that hit the instrument detector and creates these very bright points, basically. Yeah, and these halo CMEs are generally, you want to detect them early, because if they are directed towards Earth, they can cause severe damage on various assets, and Damien will talk about that in during his section. And this is why the coronagraph are used and will be used by NOAA Space Weather Prediction Center to as an early detection tool to predict the space weather and the time of arrival of that disturbance at Earth. Another mission, NASA mission, was the stereo mission. As its name says, it was to see the sun in stereo with two eyes. You had two spacecrafts. One was sent ahead of the Earth orbit and one behind the Earth orbit, trailing the orbit. And they were separating at a rate from the Earth sunline at a rate of 22 degrees per year. And that allowed to look at the sun and its corona, and also the space between the sun and the Earth. I mean, in almost real time. And the well, so here are the instruments that were on board the stereo, both A and B ahead and behind the spacecraft. You had two coronagraphs, one core one coronagraph that looked very close to the sun from 1.3 something to about 3 solar radii. Core 2 that was looking further away from the sun limb. And then two other special coronagraph called heliospheric imagers. These kind of coronagraph, they don't look straight at the sun, but they look off-centered from the sun. So they allow to observe the space in between the sun and the earth, basically. So again, we don't look, the sun is not in the field of view, but it's like at some angle. And same here for the stereo ahead, the bottom line here. So we really have a stereo view of the same events, and that has the advantage of doing some triangulation. Again, if you see the structure from 2 points of views, that allows you to using some model, determining the direction of these disturbances, and with a lot of much greater accuracy than if you had only one view, you can determine the direction of these coronal mass ejections. And here you have an example of several events that were determined with the stereo. You can also notice in that movie, so the separation was 130 degrees, and in the beginning of the movie, you have a comet. You observe a sun-grazing comet, meaning that's a comet that basically plunge in the sun and disappears. It's then evaporated in the sun. And I think at this point they observe more than 5,000 sun-grazing comets with LASCO, I think. So again, that's how the technique works. You have two images taken simultaneously of the same events, and using an ad hoc model of these coronal mass ejections, you can determine the direction of the CME. So I think this is where my section ends, and yeah. So I think I was very general on the solar corona, going from the sun, basic physics, to the corona eclipses and so on. So anyway, you can read that summary here, but in the next part, I will hand off the microphone to Damien Chua here, that's going to talk about space weather and also the next generation of coronagraphs that will be flown to do space weather predictions.
Great. Well, thanks.
So I'm going to stop sharing and maybe...
All right. Well, thanks, Arnaud, for the great introduction here. Just by way of review, we've seen that the observations from our space coronagraphs have shown us that coronal mass ejections are these transient outbursts of solar plasma, but also magnetic field from the corona. And near the sun, as we can see here in these LASCO coronagraph images, near the sun, which is this white circle here, indicates the size of the sun. The next concentric circle here is the occulter. So near the sun, the scale size of coronal mass ejections are roughly a few solar radii, as you can see out to the edge of the field of view here. I think this is a C2 image, and then I think this is LASCO C3 in the middle. But once they propagate out into interplanetary space, and once they get out to about 1 AU or 1 astronomical unit, the scale size of these coronal mass ejections can be huge. They can be about take up the space of roughly about a quarter of the ellipse encompassed by the Earth's orbit. So they really can have the scale size of the solar system once they propagate out. And in terms of how fast they go, On the slow end, coronal mass ejections can have speeds of maybe on the low end about 200 kilometers per second. Some of the fastest ones that we've observed to date can propagate through the heliosphere at speeds upwards of 3,000 kilometers per second. So at those speeds, CMEs can take anywhere from a few days or on the low end to propagate out from the sun to about as fast as 15 to 18 hours to get out to 1 AU. And as the CMEs propagate outward through the heliosphere, they're actually propagating, the faster ones, they're actually propagating faster than the background solar wind, which means that a shock is created in front of the magnetic bubble that is the CME, meaning that it's creating a shock at that front. The background solar wind is propagating outward at, let's say, garden variety solar wind propagates out at roughly 400 kilometers per second. So if you have a structure moving through that at 1,000 kilometers per second, it's going to create a shock at the front end. And that shock is where a lot of the particles associated with the CME are accelerated to high energies. And that's where we see the origin of a lot of the high energy particles that are associated with these structures. So coronal mass ejections can propagate out in all directions in the solar system, and certainly a few of those that are observed from the Earth as halo CMEs, these can and do interact with the Earth's magnetosphere. So our magnetosphere is this magnetic bubble caused by the Earth's magnetic fields, and since the Earth is embedded within the heliospheric plasma and the solar system, the interaction of the CME with our magnetosphere creates these global scale disturbances in the near Earth space environment, and that's what's being depicted in this animation from NASA. As you can see, I'll just wait for the animation to catch up here a second. You can see the CME propagating out through planetary space. During the interaction of the CMEs with the magnetosphere is compressed, and that compression can generate enhanced magnetic and electric fields in the Earth space environment. And whenever you have changes in electric and magnetic fields, that causes large-scale redistributions of the charged particles that exist within our Earth's space environment. So you have a fairly large-scale redistribution of plasma all around the Earth. And as you can see from that animation at the very end, there's also enhanced entry of high-energy particles at high latitudes. And for many of you who may be familiar with magnetic storms, what are the signatures of magnetic or geomagnetic storms is the enhancement of the aurora at around both of the magnetic poles in the northern and southern hemispheres. And you also have enhanced direct entry of energetic solar wind particles directly into the polar caps, where it's magnetically open to interplanetary space. All right, so we can now see that, as I mentioned, CMEs drive global scale redistributions in the plasma, and one region of space that we can directly observe this is actually in the plasmasphere. The plasmasphere is a region of relatively dense plasma closer to the Earth. It's sort of the the space between our charged upper atmosphere, or the ionosphere, and further regions out in the magnetosphere, where you have plasma which is co-rotating with the Earth, and it's relatively dense compared to regions further out. Well, during geomagnetic storms, which we now know are primarily driven by CME interactions with the Earth, we can observe these really large global scale changes in the morphology of the plasmasphere. So these are observations taken by the NASA IMAGE satellite, which was in operation, I think, up and through the mid-2010 timeframe. And these are observations of the helium 304 line in extreme ultraviolet. And the brightness roughly corresponds to the plasma density in the plasmasphere. And in these diagrams, the sun is at the 3 o'clock position. So on the right, you can see this depiction of the Earth here, with the white side is the day side of the Earth, and the black portion here is the night side. And as you can see through this series of images, what's happening here is that due to the enhancement of electric fields in the magnetosphere, that's basically stirring up the plasmasphere such that you have a lot of plasma that's being accelerated to higher velocity, to higher energies, and it's following this convection pattern where it's now actually starting to drain the plasmasphere. You can see this signature plume here, where during the storm, the plasma is actually being kicked out the front of the on the day side magnetosphere due to these enhanced electric and magnetic fields, which causes this depletion of our plasmasphere during these storm times. This is also associated with the enhancement of what's called a ring current at equatorial latitudes. You have a current of plasma which is going around the Earth, and we can observe that actually from the ground as a magnetic signature. So the plot that I just showed here is a magnetometer. It's a composite magnetometer trace which is measured at near the equator at a number of stations, and those measurements are combined into this magnetic index called DST, which stands for disturbance storm time. And during the storm, you can see that the signature of a geomagnetic storm is the enhancement of the horizontal component. So use your BIOS of R log, your right-hand rule, and like the orientation of if you get the orientation of this particular coordinate system right, you end up with this strong disturbance if you follow that with the right-hand rule and the right orientation of the current. So this is the telltale signature of a geomagnetic storm when you have this big dip in DST. And if we recall back to our freshman physics class, Faraday's law, we know that anytime you have disturbed or changes in the magnetic field, that's going to induce electric fields. And near the surface, these induced electric fields can drive strong currents along any paths which might have some conductivity, and these end up resulting on the ground as this phenomenon called geomagnetically induced currents, or GICs, and we'll return to that in a little bit later here. That's one of the effects of space weather that has pretty strong consequences for infrastructure and it's one of topics that space weather researchers are most interested in. If we move further down, closer to the Earth, during magnetic storms, we also see enhanced structuring in our ionosphere, or the charged portion of the Earth's atmosphere. And we can see this in this composite image. This is an image of the nighttime ionosphere taken from a series of passes from NASA's timed satellite. This is taken in UV, so you can see two main features here. You can see this band of enhanced plasma density at mid-latitudes, but you can also see the smaller scale structure embedded within it, and we'll return to that in a second. But during storms, what happens is you have enhancements again of you have disturbed electric fields, which are considerably stronger than during quiescent periods, which ends up creating much stronger plasma structures at mid-latitudes due to this fountain effect, which is illustrated here in the middle panels. So looking at, let's just take this diagram here in the middle, representing the Earth's magnetic field lines, which are running from south to north. You have in this depiction here, the electric field is into the plane of the diagram. So if we again return to our right-hand rule, if you have electric fields into the screen crossed with the magnetic fields going from south to north, you end up with an upward velocity or an upward force. So plasma is transported up near the equator, and then due to diffusion and gravitational settling, the plasma gets transported from equatorial regions to these mid-latitude regions on both sides of the magnetic equator, resulting in these enhanced plasma enhancements at mid-latitudes, particularly during storm times. These exist during quiescent periods as well, but they're much stronger during storm periods. The diagram on the right here shows some remote sensing observations that our division has made of these structures. So this is the panel on top is a remote sensing observation by a limb scanning spectrometer, which is used to back out these electron densities, and this was just a modeling run of simulating these particular sets of observations. Going back to these small scale structures, you can see that within these bright regions, there are these smaller scale regions as well, and these are small scale plasma bubbles. These are actually regions of depletion of plasma. So they're highly structured, as you can see. The images in the center here are taken from all sky camera images. These are in white light taken from the ground at various locations. And you can see that there's actually very small scale structuring within the enhanced plasma density, where you have these voids of plasma and very strong gradients of electron density through here. And these are caused by plasma instability, basically an overturning instability, where you have when you have higher density plasma sitting on top, there's a plasma instability that's basically an interchange where you have plasma being transported from higher altitudes to lower altitudes. And it creates these voids, and these voids are significant for space weather because these have been strongly associated with radio frequency scintillation. As you can imagine, trying to pass a radio wave through this, and that RF transmission is experiencing fairly significant gradients in density as they cross one of these structures. So a pretty major space weather effect that has generated a lot of interest over the years. And we'll return to that in a second, but just for to talk about some of the broader space weather impacts, I did mention the effect of the phenomenon of ground-induced currents. Well, this has had a fairly significant, they can have significant impacts on things like power transmission. There was a fairly well-known incident back in 1989 when a magnetic storm took out the power grids in Quebec, and I guess that was experienced through the greater part of the Northeast as well. It can also, one of the other major areas of impact is on navigation systems, GNSS and GPS specifically, as one of the major concerns during space weather events. There was particularly well-studied one during October 2003 during the so-called Halloween storm, when the FAA's wide area augmentation system went down, and that's kind of illustrated by these this plot here on the top, showing basically red is bad, where there was no availability of this navigation augmentation system provided by the FAA, and that was strongly associated with this region shown on the bottom here of where the plasma gradients were largest in the ionosphere. We'll come back to, I already mentioned the impacts of HF radio communications. That is a concern over large regions. Like there was this example where during magnetic storms, you typically, or you can experience broad outages of HF radio, which can cause blackouts across large regions, which can affect operations of airlines, which then have to be diverted away from polar routes. There was an example cited here back from 2005. And if I guess one of the first things that I noticed at space weather conferences was the presence of representatives from airlines. So they're quite tuned into to these studies and the observations that feed them. There was the last effect here that I'll mention is the effect of satellite drag. So as you have these redistributions of plasma in the ionosphere, what you also get in association with that is actually an expansion of the neutral atmosphere due to heating of the upper atmosphere. And what that can do is enhance the amount of atmospheric density you have at higher altitudes that you would normally, under normal conditions, not have. This effect of enhanced upper atmospheric densities creates additional drag on any satellites or spacecraft that are flying in low Earth orbit and who happen to be flying through these regions. enhanced upper atmospheric density, and this effect was attributed to the event where SpaceX lost a number of their Starlink satellites back in 2022, which was associated with a period of geomagnetic activity where I believe they deployed their satellites during one of these magnetic storms when there was enhanced upper atmospheric density, and that deployment clearly did not go well due to this unforeseen or the effect of enhanced drag on the satellites that were deployed. I just wanted to give you another example, going back to the HF propagation and radio frequency outage. This is a plot of effectively plasma density. The color scales are actually plasma frequency, but that's proportional to plasma density. And this is the y-axis here is altitude, and this is latitude. So this is a north-south cut of the ionosphere over Afghanistan. This was taken from a study by Kelly et al., who looked at this one particular incident during the Afghanistan war, where there was during the Battle of Tucker Gar, during Operation Anaconda, during that, let's see, when was that? 2002, when we had forces on the ground that lost UHF SATCOM capability during that conflict, and the analysis following that showed that their line of sight from the ground to where the communications satellite was directly passed through one of these plasma bubbles that I described before. So this was one of the first published incidences where there were real impacts associated with space weather on operations. So all of this, our ability to plan and predict the occurrence of geomagnetic activity and storms in particular basically comes down to detecting the emergence of CMEs from the sun. And I kind of like to use this tropospheric analogy to illustrate the way that we're trying to employ remote sensing techniques like our coronagraph observations. And it's analogous to how we detect hurricanes out in the Atlantic. So just as a thought experiment, imagine a situation where we didn't have any geosynchronous imaging like those provided by the NOAA GOES satellites, and we only had nearshore observations, maybe some sounding balloons and the like. So we have no knowledge of any activity beyond our line of sight from the shore. So we really only detect hazardous storm conditions as they make landfall, and there's no capability to forecast or predict that. But of course, in the real world, we do have these NOAA satellites that provide these wide field imaging of the Earth from geosynchronous orbit, and we use these to great effect every hurricane season to detect the formation of these storm systems out in the Atlantic, and then use those data to predict the path of the hurricanes as they propagate closer to land. And of course, we feed these observations into weather models, and those help us to create actionable data and a forecast to help operators and civil authorities to plan accordingly. And this is essentially what we're now trying to do out in the heliosphere with the coronagraphs. So as Arnaud mentioned, we've been using and deploying coronagraphs for a number of years in space. These are just two examples that were mentioned before, SOHO, LASCO, and Stereo SECI. But in order to take the next step to transition what we've learned over decades of research into something that can be deployed operationally, we were tasked by NOAA to study coronagraph designs to attempt to make the coronagraphs somewhat easier to deploy. As you can see from this illustration here, the research grade coronagraphs are quite large. They're over a meter long, which once you package them up into a payload, create quite unwieldy instruments to fly, especially if you're looking at multiple flights. And if you're trying to deploy a fleet of spacecraft to make observations, what you really want to do is to be able to make something much more simple, much more well, compact, which is how we got to the C-Core, the compact coronagraph design. This is just a comparison of the traditional research focused coronagraph on Stereo SECI. It's about 1.4 meters from nose to tail. And we've since come up with a combination of clever optomechanical design by folks like Arnaud, and some basic folding in some first principles diffraction physics. We were able to come up with the design with essentially comparable performance of Stereo SECI in a package that was effectively half the size. And this was what we essentially did was, you can see this illustration similar to what Arnaud showed of the optical path of a conventional LEO coronagraph, with starting with the external occulter, going through the objective lenses and the various field stops to block out stray light. There is this LEO stop here to effectively take out stray light that results from all of the optical components ahead of it to then create your coronagraph image. Well, we essentially threw out most of this, and we were able to accomplish this by instead using this multi-disc occulter. So we're effectively using a series of occulters here, each one blocking the diffracted stray light from the one just ahead of it, which is using this arrangement able to then achieve comparable stray light rejection to be able to pull out that important K corona signal. So at the Naval Research Lab, we've been contracted by NOAA to build a series of these compact coronagraphs. The first one Secor 1 will fly on the NOAA GOES-U satellite. There's a even though most of the payloads on GOES-U will be Earth pointed, there is a solar pointing platform right at the base of the solar array yoke, which is sun pointed with a suite of sun observing instruments. And GOES-U will be the first one to include an NRL Secor instrument. So GOES-U will launch this summer. I believe June 25th is the current launch date from Cape Canaveral. Secor 2 is going to, the second in the series here, is going to launch on NOAA's space weather follow-on spacecraft, which is going out to the first Lagrange point, or the L1 point, which is the gravitational balance point on the sun-Earth line between the Earth and the sun. So it's a point. It's a virtual point along that line in which the gravitational forces are balanced between the sun and the Earth, and you can send a spacecraft there and park it in a fairly stable orbit at that location, which makes it a fairly ideal one for making long-term observations of space weather. That's effectively where many solar missions are orbiting, including SOHO and others, the ACE spacecraft, and next year the SWIFO spacecraft will follow along with that. SWIFO is actually it's a ride share. It's a secondary payload that's hitching a ride to L1 with the NASA IMAP mission, and we anticipate this launch sometime in the middle of next calendar year. The third one in the series, and one that we're in active development right now, is the Secor. It's going on ESA's Vigil mission. Vigil is similar to SWIFO, except that it's going out to the fifth Lagrange point, which is another quasi-stable gravitational balance point that is at the same distance from the sun as the Earth, but it's located 60 degrees trailing the Earth's orbit. So if you can imagine equilateral triangle from the sun, the Earth, and this L5 point, the L5 makes the third point in that equilateral triangle. So the L5 point makes for a fairly ideal spot, because you can park a satellite there and make continuous observations from a slightly different vantage point. This is just a cutaway view of the that which shows you kind of the guts of the Secor instrument. This is Secor 1 here. So we have this at the front end, the sunward pointing side, this reclosable door, which we can close and open by command. Here we have the coulter. This is the heart of the instrument, which is the device used to block the disk of the sun. And then next we have the first aperture here in front of the lens barrel, and then the lens focuses the image onto this active pixel sensor detector, which is a CMOS detector device, kind of similar to the ones in your phone, similar to a CCD, except that each pixel can be read out individually. So a relatively new application for this class of detector in space. This is just a snapshot of the installation of GOES-U onto, installation of CCOR1 onto the GOES-U solar pointing platform. And it's our lead mechanical tech, Steve Tanner, shown there. And this is what we anticipate the CCOR1 images will look like. This is a simulation of CCOR image by using a LASCO C3 image and scaling it to using some modeling to scale it to the brightnesses that we expect to have in CCOR. So you can see in this movie on the right here, the emergence of this halo CME. We're using simulations like this to give us some confidence that we will in fact be able to pull out the CME signal and detect them out to our edge of our field of view. So what are we going to do with this CCOR data? So as I mentioned, we will be using NOAA will be using the CCOR data to detect and also track coronal mass ejections. If you take 2 subsequent chronograph images and you measure by your favorite means the edge, the leading edge of the CME in 2 different images, you can then just simply compute just you can estimate the velocity in at least in the plane of the sky, the velocity of the CME, and then also be able to derive the direction of the CME as well from the image data, and also be able to using some modeling parameterize some other aspects of the coronal mass ejection structure itself, like its width. And you can also, from the brightnesses, infer some information about the plasma densities, at least through the line of sight. And then using that, get some estimate by applying some modeling to how much mass is represented within that plasma structure. Ultimately, the images will be used to derive forecasts, space weather forecasts of CMEs at Earth. So this is output that you can see examples of from NOAA's Space Weather Prediction Center website. This is representation of the heliosphere from this solar wind heliosphere model, the Wang-Shili-Enlil model, or WSA-Enlil. So here you've got in this movie, you've got the top here is plasma density with the sun at the center. These circles here are, this is 1 AU at this distance. I think that's Earth, stereo A and stereo B. The bottom plot is the radial velocity, so the velocity of the plasma as it's moving out. And then shown here are just some parameters of the plasma predicted by the model. And so, small plane as it at these locations. You can see in this model run the propagation of that CME structure captured by the model. So ultimately, the CCOR data will be used to initialize the model runs like this once CMEs are detected. Their studies have shown that the inclusion of CME or the inclusion of coronagraph observations and the detection of CMEs from them have improved the prediction of geomagnetic storms at Earth fairly significantly. Granted, these numbers in the absolute sense maybe aren't terrific, but from 27% to 60%. But given the fact that space weather forecasting is probably at least a few decades behind terrestrial tropospheric weather forecasting, that's still a pretty remarkable result just from the inclusion of CME imagery. But it's also led to the reduction in the uncertainty of the predicted arrival times of CMEs at Earth fairly significantly. Won't say much about this table. This is just giving some performance parameters of the various C-cores, just saying that we observe in white light, and we're looking, C-core will look from about 3 outwards to about 22 solar radii for C-cores 2 and 3. And the image cadence is about 1 minute, 1 image every 15 minutes or so, with about roughly 15-minute latency from when the image is taken to when it's transmitted to the spacecraft. I'm going to go back to where the C-cores will be located. As we mentioned, we're going to have C-core 1 sitting at geosynchronous orbit. We're going to add a second C-core out at L1. So this is just an illustration of looking down at the ecliptic plane, the sun and the Earth here. So we'll have 2 views of the sun from near the Earth, which will detect CMEs from that vantage point. Mostly we'll see those as halo CMEs, as we saw in the examples. If we add C-core 3 at Vigil, on the Vigil spacecraft from L5, we'll also have a third vantage point, which is very advantageous because we're now looking across the Sun-Earth line, which will then create sort of a transverse view of the CMEs as they propagate out. And the combination of these observations will allow us to better triangulate the direction and speed of these structures as they move out from the sun. Another distinct advantage of L5 is that some of the other remote sensing instruments will actually be able to see structures on the solar disk before they rotate into the field of view from the Sun-Earth line, which is a capability that we have not had before. At present, from the Earth, we can only see things like sunspot groups and things like that as they rotate into our field of view. But from L5, we'll be able to see past the limb of the Earth, as the limb of the sun as seen from Earth. So that's another huge advantage. This is just a snapshot of the C-core 2 instrument on SWIFO, and yeah. I think an early depiction of C-core 3 on Vigil from such in conclusion, as a summary, CMEs are a fairly common phenomenon. Some of these can be directed towards the Earth. They can induce pretty strong effects in the terrestrial environment that can affect and damage a lot of the critical technological infrastructure in which our society currently relies upon, such as satellite communications. navigation, and certainly, as I mentioned, the effects on our power grid. And one way that we are trying to predict the occurrence of these is the use of spaceborne chronographs like CCORD to detect the occurrence of these phenomena and to enable the tracking of these as they propagate out through interplanetary space. And we've been able to do that by leveraging our experience in doing making chronograph observations for basic research, and trying to transition that capability to enable operations using those images in an operational sense. And we're certainly looking forward to working with NOAA in deploying these in the near future, hopefully very soon. So yeah, thanks for tuning in. And if you would like to know more about our chronograph work, these are some websites that you can visit, including some at NRL, but also those websites called out there, NOAA's Space Weather Prediction Center, and more on the research side, the NASA heliophysics page. So, I'll wrap it up there, and I guess we'll can move on to any questions that you might have.
Well, that's great. Ed had, I don't know if you saw, but Ed had a question in the chat that was answered, but if you haven't seen it, Ed was asking about the imagery from these instruments, and I guess the answer to that is that the images are going to be available on NOAA as well as some other websites as well.
Yeah, ultimately the data will come down through the NOAA's ground processing system, and they should be made available publicly through NCEI, which is the National Center for Environmental Information, I think.
Okay. I did have a question in regards to CMEs. In the past, it seemed like the power companies were pretty unprepared for any kind of major event. I think you mentioned 1989, and there was a big eruption in 2003, and they've become more aware of it. Do you think that the power companies are prepared for a big event should it occur?
Yeah, they're certainly paying much more attention to it. They're also this is one thing that's discussed a lot at conferences like the Space Weather Workshop, where they, in terms of their concept of operations or their ConOps, during an event, they can redirect traffic power distribution on the grids if they are given information about when and where events like this might occur, or the areas of impact of one of these, which is tough given how interconnected a lot of the power grids are.
Right.
It also requires probably a little bit stronger coordination between various power grid operators.
Right. And I remember speaking to someone from one of the power companies here in New Jersey, and they talked about how they had started to build sort of backup equipment like transformers. Apparently they when the 1989 event happened, I think they kind of felt they had got caught with their pants down, because it takes
Right.
a long time to build one of those things.
It
and
does,
so I think
yeah.
they had started to build some backups. I don't know how many they have prepared, but hopefully they could are prepared for a major event, you know.
So I have a question related to that. What do the satellite operators do to prepare?
Yeah, so the concern from satellite operators is, I think, mainly from the perspective of energetic particles and the penetration into the satellites themselves. You can sort of engineer your way around that to some extent, but there have been some well-documented cases of satellites experiencing more than single event upsets, essentially having their electronics fried by energetic electrons. And so I think in those cases, the standard operating procedure tends to probably just be to power down and then power them back up after the event. In the example of the satellite drag, yeah, I'm not quite sure what solutions exist there in terms of mitigating that. There's only so much maneuverability you have on orbit with the satellite in LEO. It's probably in that case more a problem of having the knowledge to then correct your the ephemeris of each satellite as they're traveling through their orbit, and to be able to know where they are.
Thanks.
To further expand on that same question, 1989 was pre-ISS. Did they have contingencies to deal with that, as far as like systems failures while they're occupying the space station?
I do know that they have contingencies for relocating the occupants of the ISS during storms. Like they shelter. There's a sheltering procedure that they have where I believe they shelter it in portions of the ISS that are shielded, just in terms of astronaut health. But in terms of the overall effect of the entire station, I'm not sure what precautions from a procedural standpoint exist. I know they do have some orbit raising capability, some maneuverability, but I'm not sure in terms of specifics.
Okay, thank you.
I have a question.
Sure, go ahead.
Hi, I have a question. This is Jeff. I was curious what types of particles are contained in the ejections. Is it just electrons, or is it many other types of particles?
So in terms of the energetic particle species themselves, yeah, mostly the vast majority are just energetic protons and electrons. There are minor species of other ions that exist in both the background solar wind, but also associated with these CMEs. Arnaud, do you want to take a stab at some of the minor ion species that folks
Yeah,
like.
I'm really not a specialist on this question, so yeah, I cannot really answer more than what you just said basically.
But there are other like heavier
Yes,
ions, helium, oxygen, all the way
yeah,
up to iron and magnesium um, that can be
yeah,
observed.
yeah, yeah.
And there are various, I guess, depending on the state of ionization of each ion, there can be various effects in terms of how they're accelerated. Folks like Martin Lamming are well versed in the
Yeah,
subject
yeah,
of
we have some very yeah, some specialists at NRL, yeah, that
right.
would really answer that
Yeah.
better than me at least.
The aurora borealis is created by electrons that are hitting the magnetic field. Is that true?
Yes. So yeah. So the aurora, I'd either hold it's created by predominantly electrons that are precipitating from the Earth's magnetosphere into the atmosphere or atmosphere, typically in um, the E to F region of the ionosphere, which is in say like the 100 kilometer to 1,000 kilometer altitude range.
Okay.
And what happens is you have electrons precipitating down, and they'll collide with something like a nitrogen or an oxygen atom, and there's various excitation mechanisms that then result in the light that we see as the aurora. So the fairly familiar green color that you see in a lot of auroral pictures, that's
Right.
from oxygen. That's it's a emission at 557.7 nanometers. The
Is that O3?
5537. I think it's atomic oxygen.
Oh, okay. And if electrons cause the aurora, what effect would protons have?
Protons actually precipitate and create aurora as well, but from a slightly different mechanism. It's a proton will precipitate, and actually it's a mechanism of charge exchange. So that proton will combine with the free electron, and it'll turn into a hydrogen, excited hydrogen atom, which will then you can observe that those protons through actually the Doppler shift of that excited the light emission from the excited hydrogen atom. You can observe that as a Doppler shift. You can observe the Doppler shift in that as the emission. And I think there are other excitation mechanisms that are caused by protons precipitating as well. So you can have both, but it's clear the bulk of the emissions from the aurora are due to precipitating electrons.
Okay.
And
And
you
these
can see,
images of, I'm sorry, go ahead.
I was just going to say you can observe these auroral emissions all the way from X-ray all the way through kind of the near infrared. So it's a fairly, even though we see them visually as like the dominant green lines, or sometimes there are some kind of bluish and purple lines associated with nitrogen emissions, but they go all the way into the UV and X-ray as well. Especially with
I
the
see.
really energetic electrons, you can see Bremsstrahlung emission as X-rays from aurora, from
Cool.
the breaking of the energetic electrons. These are like several tens or hundreds of keV electrons as they get stopped in the upper atmosphere. They produce X-rays, just kind of cool.
Mm-hmm. And I'm looking at this image that you have up there of the corona. Is that something that an amateur can capture?
Which one? The one on the left or on the right?
On the left side. It's a beautiful image, and if we could block the if we could insert an eclipse, as some of your instruments do, in front of a telescope, could we capture something like that? And what wavelengths is that? That's visible light there, right?
That looks like a simulation, Damien. That NASA GSFC.
Yeah,
I'm looking on the left.
Yeah, that one. I'll have to double check. That might be a simulation. Looks a little bit too clean for an actual image, but
Yeah,
case in point, I think yeah, I think maybe going back to maybe one of the first ones that you showed,
yeah, the
Arnaud,
first images that they were real images. Yeah, yeah. If you go back to
let's go back pretty far.
yeah, this one.
Like this one. Yeah.
So this one is a real image. So and actually, you have the name of the person, Nicolas Le Photo. You can contact him and you can probably ask him how he obtained that. But my guess is that okay, he has a very good camera and telescope, and that image has been processed, in my opinion. You know, it looks like there was some uh, sharpening of the image. That's my guess. But that's
Okay.
yeah, that's an amazing image, and you see the stars even. You know, the sky is so dark that you see some stars in the background.
Right.
And my guess is that he was at a very good location because the humidity was probably very low, and maybe he was at some altitude, at some high elevation. I don't know, but again, I think you can contact him. If you
Okay.
Google him, you will find him, I think, because I contacted him to have his authorization to use his image here.
Okay. Thank you.
But that can only be taken during eclipses. You also have some ground-based chronograph. I think I forgot the names. I'm sorry, but yeah, there are some. I think one is based in Colorado. I think it's
Yeah,
Mark 5 or Mark. I forgot.
and there's one on top of Mauna Loa in Hawaii
Or
as
maybe
well.
it's the one on top of Mar. Yeah. So I'm yeah.
Yeah, I think the one that you mentioned is in Hawaii.
It's in Hawaii. Okay. I actually had a list that I didn't present here, but I have a list of the ground-based chronograph as well. And they can get similar images, you know. Um, um, but I don't not as good, but they are quite usable for sure.
Yeah, the ground-based ones, because they're not limited so much by payload mass per se. Their observations can get very close to the limb of the sun.
Yeah.
Like they're at like 1 point something our
Yeah,
sun.
1.1, 1.2. Yeah, yeah, very
Yeah.
close.
Mhm. Okay. Thank you.
Hey, any other questions? Well, if there's no more questions, we want to thank our speakers for a wonderful talk. And so thanks everyone for joining us. And we're going to move into our business meeting next. So members, please hang around and we'll see you next time. Remember that for those of you who might be tuning out at this point, we do have our next meeting in May is going to be our student showcase, so to speak, where the students are going to be giving presentation on their research projects. We'll have some Montclair State students. Or we have, Mary Lou, we're going to have some students from some of the other colleges this time?
Yeah, we'll at least have somebody from NJIT.
Oh, right,
Yeah.
great. Okay, so that'll
Yeah.
be next
That'll be
month
fun.
in May. So yeah, so please do join us in May.
Okay. Well, thank you very much. And we wish you well in getting these pieces of equipment up into the spacecraft, into the sky.
Yeah,
Very
stay
good.
tuned for the first images, probably September, October next year. Well, no, this year. So
This year.
Very
Great.
good. Very good. Okay. We look
and
forward
thank
to
you very
that.
much for inviting us.
Thank you very
Thank you.
much. Bye-bye.
Thank you for having us. Thank you.